So in this video, I want to do a quick review of Lewis structures and introduce this concept of formal charge. Okay, different people have different ways of introducing Lewis structures. I want to talk about a quick way that you can do most molecules that contain some fairly common elements: hydrogen, carbon, nitrogen, oxygen, and halogens. All right. So if you're used to a different way of doing this, that way will still work, but this is something that works very well with especially drawing organic molecules where these are the common elements. So the common way to do this is to first start by drawing the neutral atom fragments. All right, and this is done just by drawing the atom symbol and then drawing a dot to represent the number of valence electrons that the atom would have. All right, so for example, so first of all, you can find the number of valence electrons by looking at the position on the periodic table. So again, a quick way to determine the number of valence electrons that an atom would have is just to look at its position on the periodic table. All right, everything here would have 1, 2, 3, 4, 5, 6, 7, 8. Remember, you skipped the middle section of the periodic table in determining the number of valence electrons. And what we're going to do is we're going to place the electrons around the atom so that you do it so that you always put one dot on each side before you ever double up. All right, so for hydrogen, there's only one dot. This would be the only way that you could draw it. Notice that you could put the dot on any side of the hydrogen that you wanted to. We just happen to put it on the right side here. Okay, carbon, this would be the only way to do it. All right, notice that this, if I draw it like this, even though it has the correct number of valence electrons, this would not be an acceptable way to do that. So I'm going to put that, mark that out, because in drawing it that way, you're doubling up on two sides before some of the sides have any electrons. All right, so that would not be okay. All right, nitrogen would have 5. This right here would be acceptable. This right here would be acceptable, but this right here would not be acceptable. All right, so get used to the idea that if you have 2 on any sides, you need to have at least 1 on all the sides. All right, so that's not going to be good. All right, neither would this one right here for oxygen. Oops. All right, so you do have some freedom in how you draw these, but there are some incorrect ways. All right, so let's practice this with this formula right here. First thing that we're going to do is just lay out the fragments, and we're going to start just by trying to link things together. All right, so the first thing that we could do is take these 2 carbons. We'll link those together. All right, notice that when you link 2 things together, you should still have the same number of valence electrons as just adding up the sum total of the individual parts. So there's a total of 8 electrons between these 2 carbons. There should be a total of 8 electrons here. All right, we could link in, from this point, we could take this oxygen fragment right here, and we could pair things up over here. So we're at this point right here, we're going to add in these 3 hydrogens. And then what you get to is a situation where we've added in chlorine as well here. And we get to this situation where we've used up all of our atoms, but we have this one single electron here and one single electron here. And what we can do is we can have those come in and make another shared pair. All right, so that's why here you have the single electrons, but only one pair between the carbons. And here, those single electrons are gone, but you have 2 pairs. All right, and so from that point, what you can do is anytime you have shared pairs, you can represent those shared pairs as lines. All right, and that's what I've done here. One thing, since this is an organic molecule, we can show this as a line angle drawing. And in a line angle drawing, this is where you do not show any of the carbons, all right, and you assume that there's a carbon at either any intersection or any blunt end, all right, and you then fill in for any missing hydrogens off of those carbons, all right. So this would be the line angle structure for this particular structure. And I wanted to point out that for this particular formula right here, there is another way that we could have correctly connected the atoms. All right, this is an acceptable Lewis structure for it, but this right here is also an acceptable Lewis structure. All right, there's also other acceptable Lewis structures And that's one of the things, especially when we get to organic chemistry, you'll realize that there's more than one correct way that you can draw a structure. So in the past, you've been introduced to polyatomic ions. And we know that these are molecules where the overall molecule has a charge. All right. For example, ammonium is NH4, but that has an overall +1 charge. And you indicate that by putting the charge with the formula. Another example would be something like carbonate, CO3, with a -2 charge. All right. So the thing about that is, even though we normally draw these polyatomic ions by their formula, they also have Lewis structures. And within their Lewis structure, it's possible to identify the particular atom where that charge would primarily reside. All right, that's a little oversimplified, but let's go through the process of how that works. So let's first of all assume that we had ammonium, which is NH4. All right, so another way of drawing an ammonium ion would be to draw it as a Lewis structure like this. All right, where I've drawn the nitrogen in the middle and I've drawn 4 hydrogens, each single bonded. And what I've done here is I've just said, okay, this entire thing has got a +1 charge. All right, but let's say that we wanted to figure out which one of these atoms is the one where that charge would primarily reside. All right, so the way to go about doing this is we're going to make use of these of the number of valence electrons that we know the neutral atom should have. All right, so what we're going to do is we're going to take each bond and we're going to split it apart. All right, so we know that each of these bonds contains 2 electrons. And if we split it right down the middle, and we're just going to assume 1 electron is going to go with one atom and 1 electron is going to go with the other. All right, if we split all these bonds up, we would end up with all of these different pieces. All right, so the 4 dots that come around this nitrogen, 1 comes from this bond, 1 from this bond, 1 from this bond, 1 from this bond. All right, so I'm going to call these atom fragments. All right, and so what we're going to do is we're going to compare the number of dots, or the number of electrons around these atom fragments, to the number of dots that the neutral atom should have. All right, so when I'm taking this right here, there's only 2 types of fragments. There's the hydrogen fragment and that nitrogen fragment. All right, so if we compare that hydrogen fragment to what we know a neutral hydrogen should have, all right, notice that the fragment has the exact same number of dots as the neutral atom. And what that does is that proves that the hydrogens in the structure would be considered neutral. All right, but if we take that nitrogen fragment, notice there's 4 electrons, but we know from previous experience that nitrogens, actually I haven't shown nitrogen, actually I showed it up here. Yeah, nitrogen has got 5 electrons around it. And so that's got 5 electrons. So this right here we can see has 1 too few electrons. All right, it would need 1 more electron to be neutral. So therefore, if it's got 1 less than what it needs, it would actually have a +1 charge. All right, so when things have too few electrons, they have positive charges. When they have extra electrons compared to the neutral atom, they're going to have negative charges. All right, so so what that proves is that the nitrogen here has the nitrogen would have a positive charge. And the way that you indicate that is you draw the molecule and you put a little plus charge beside the atom that has the charge. All right, so I wanted to do this as practice. I didn't cover up the answer. So hopefully you'd be able to see that with this particular example right here. If you split these apart, the hydrogen would have 1 dot. The oxygen would have 1, 2, 3, 4, 5, 6. So it's got 6 from the lone pairs that you're showing. But then it's going to have 1 extra one from this bond right here. Remember, each atom takes 1 of the electrons. All right. So that oxygen would have a total of 7. That's 1 more than the 6 that it needs to be neutral. And therefore, it's got a negative charge. And we would indicate that with that little minus there. All right, so notice on Lewis structures, there should be no atoms with higher than a +1 charge or lower than a -1 charge. All right, it's possible to draw things with those, but the proper Lewis structure will not have anything higher or lower than +1 or -1. So earlier we did a little shortcut to drawing Lewis structures I want to do a quick review of the more general way of doing this. Even though, like with most organic molecules, you won't have to do this. For certain molecules, this is the way that you're just going to have to go about doing these Lewis structures. Okay, so first of all, count all of the valence electrons that are in the structure. All right, and I mentioned don't forget to add or subtract valence electrons to account for the charge. So first of all, we're going to take this particular formula, C2H5O, with a negative charge. And, well, each of the carbons is going to have 4. Each hydrogen's got 1. There's 5 of them. That's why we're going to do 5 times 1. We've got the oxygen, which has got 6. There's only 1 of them. That's why I'm just showing a 6 there. And then notice it's got a negative charge. So that means that this structure is going to have 1 extra electron. Because remember, these are the number of valence electrons that the neutral atoms would have. All right. So if we add all those up, we're going to get 20. So the next thing that we're going to do is we're going to connect, determine the central atoms. All right. Sometimes there's different ways you can put these together. Usually it's going to be the one there's only 1 of. In this one, we're not going to have just 1 central atom. When they say determine the central atom, it's something like NH4. All right, where obviously then the nitrogen would be the central atom. Next, we're going to connect all the atoms with single bonds, and that's what we've done right here. All right. We're going to then fill in the remaining electron as lone pairs around the atoms. All right, so let's count how many bonds or electrons we have when we do this. We've got 1, 2, 3, 4, 5, 6, 7 bonds. That means there's 14 total electrons accounted for when we connect things with the single bonds. All right, so that means we need 6 more. All right, and the way that we're going to do that is we're going to find atoms that can accommodate more electrons, and the oxygen is going to be the one that can do that. So there, and there. All right, so this would be the acceptable Lewis structure. All right, so it is possible that you can, if you have enough practice with doing the previous method of doing this, and you just realize, okay, we need to add in 1 more electron for that charge, where you could use this shortcut. Either way that you feel more comfortable, as long as you get the correct answer, is fine. All right. There are this next case is one where you probably are going to be using this method right here. So we're going to do sulfate, which is SO4, and there's overall a -2 charge on it. All right, so let's first figure out the total number of valence electrons. Sulfur would have 6. We've got 4 oxygens. That's going to be 24 total electrons plus the 2 extra from the charge. All right, we add all those up and we get 32 electrons. So the next thing that we're going to do is we're going to determine the central atom and connect all the atoms with single bonds. All right, so with this formula, it's pretty easy to determine that the central atom is going to be the sulfur. Put that there. Let's connect everything with single bonds, and if we count up the number of electrons so far, that's 8. All right, but we know that we need a total of 32. So what that tells us is that there's 24 extra electrons. In another way of saying that is 12 more lone pairs that we need to place somewhere around this molecule. And when you're doing this, the easiest thing that comes to mind for me is just to place them all around the oxygens. All right. Keep in mind that the place that you originally put them is not necessarily going to be the place that they are in the final molecule, but we'll deal with that in a second. So after we take those 24 additional electrons and we place them on atoms around the molecule, you would have a structure like this. Okay, so this is where you need to deal with the last step. All right, you need to calculate the formal charge on the atoms, and after you do that, you want to share electrons to minimize the number of atoms with formal charges. Okay, that reminds me, there should actually be a minus charge on this oxygen right here, because if we calculated the formal charge around that oxygen, it would be -1. Okay, so when we do that for this particular atom, you'll notice that on all of the oxygens, you would have a negative formal charge. All right, and around the sulfur right here, if you break that apart, there's 4 dots around it, but sulfur needs 6 dots or 6 valence electrons to be neutral, so there would actually be a +2 charge on that formal charge on that sulfur. All right. So the thing about drawing these structures appropriately is you want to share electrons to minimize the number